This is a discussion about AVL trees. I will assume you know what a binary search tree is. An AVL tree is a special kind of binary search tree that is annotated in such a way that the tree stays balanced, or reasonably balanced enough so that its depth is going to be such that all the operations are efficient because the depth never gets too large. And the math behind why that is true will leave for someone else. This is basically a discussion of what an AVL tree is and what its operations are. So fundamental to an AVL tree is this notion that you can rotate certain nodes over one another and maintain the sortedness property of the AVL tree. So here is an example of a binary search tree. These red trapezoids here indicate subtrees, and what's written on the trapezoid is constraints in terms of what the values must be. Anyway, so for example, I have 17 here. That means that everything in the left subtree is itself a binary search tree that whose values are less than 17. Because the root here is at 28, that means that the values here are going to be between 17 and 28. If they're integers, they'll be in the range 18 to 27, etc. Now this particular binary search tree kind of goes off the right and kind of gets kind of deep, and that's one of the problems with a binary search tree. If, for example, you insert your elements in order, you're going to get a very lopsided, unbalanced tree. So the idea of a tree rotation is that you can rotate one node over another, and it's a constant time operation. It ends up taking 3 pointer swaps, and then you can, it's basically a 3-way pointer swap, and it can make the tree more balanced but maintain the sortedness property of the tree. So let's look, for example, at the 46 and the 64. Okay, because of their position, that means that the 64's left subtree has values that are in between 46 and 64, by definition of a binary search tree. And so what we can do is we can rotate the 64 over the 46, and that is done by taking 33's right subtree pointer and having it point to the 64, have 64's left subtree pointer point to the 46, and have 46's right subtree pointer point to this subtree. So it would look something like that. And so the sortedness property of the tree is not changed. Here, 46 is left subtree. These guys are all less than 46. It's right subtree now. Well, these guys are kind of between the 46 and 64, just like they would have been before, etc. So by doing a rotation of one node over another, so a child over its parent, you can change the shape of the tree, but still it's a binary search tree, and it's a constant time operation. It's basically a 3-way pointer swap. And so you could continue doing this, doing some rotations, and by doing rotations, you can make it a much more balanced tree. So the idea of an AVL tree is that we're going to insert elements and delete elements just like we would in a regular binary search tree, but we're going to keep enough information around so that we're going to know when it is a good time to do a rotation that keeps the tree balanced. So what is an AVL tree? An AVL tree is a tree where every node is annotated with its balance. And what its balance means is if I compare my left subtree with my right subtree, which one is higher? And a constraint on an AVL tree is that any given node, its left subtree and right subtree's heights can differ by no more than 1. So for example, here I have a 66. Its left subtree, this is a tree of height 2, 1, 2. Its right subtree is a tree of height 1. If 87 is the root of the subtree, There's only one level below that. And so we mark it as being left balanced. And the marking here, this large blue circle here to the left, indicates that this tree is left leaning. If I look at the 29, it is right leaning, okay, because its left subtree has height 0, its right subtree has height 1. And so I mark it there. The 87, its left subtree is null, its right subtree is an element, and so it's right leaning, etc. But if I look at the 41, its left and right subtrees are the same height, and so I do not mark it as left leaning or right leaning. That means it is a balanced subtree. And any leaf node is going to be balanced because it has no nodes, so both subtrees are null and therefore the same height. Okay. Many implementations of AVL trees that I have seen, in fact most of them I've seen on the internet, do not keep track of the balance explicitly. Rather, each node keeps track of its own height. And the way you determine whether a tree is balanced or left leaning or right leaning is you look at your two children and look at their heights and compare them. That works. To me, it's a little inelegant because it takes more space. For an integer, it takes more space than a three-way value, or actually an AVL tree can be implemented with a Boolean where each child is annotated with am I a higher child than my sibling. But it's perfectly fine to implement it where you put the height in explicitly. But I think it's more elegant to just annotate them with left-leaning, right-leaning, or balanced. It takes up less space, etc. When you're keeping track of the heights, as you're doing operations, you're constantly recomputing heights on the way back up, and it just, to me, seems a little less elegant. So I'm going to do this presentation where we are explicitly representing left-leaning, right-leaning, or balanced. Okay, so this is an AVL tree. So what are the AVL operations? Well, insertion and deletion are done just like in a normal AVL tree, except when you do an insertion or deletion, on the way back up, you are going to adjust your balance factors based on the changes that have happened in the tree. And also, sometimes when you're trying to adjust your balance factor, you realize I'm out of balance by more than one, in which case you do a rotation or sometimes something called a double rotation. So let's look at some examples. Okay, let's insert this 5 into this AVL tree. Okay, well, we do some comparisons and we'll end up seeing the 5 come down here. Okay, so the 16 had seen its left subtree before the insertion as being null. After the insertion, it is non-null. That means the 16's left subtree has grown by 1. It was balanced. Well, when you insert something and that subtree grows by 1, you change the balance factor in that direction. So 16 was balanced. I've increased the height of the left, therefore I now mark it as leaning to the left. The 29, we have recursively come and done this. So the 29, before it inserted the 5 into the 16 subtree, would have looked at the 16 and said it was balanced. But now it looks at its left subtree and says it has changed from balanced to unbalanced. Well, when an insertion happens, it causes a tree to go from balanced to unbalanced. That means that subtree has grown. And so the 29 will recognize that the 16 has grown. Therefore, the 29 changes its balance factor. In this case, it's right-leaning. It is now going to change it so it is balanced. The 66 had inserted the 5 into the 29 recursively. It had seen it as being unbalanced at first. Now it's balanced, but that doesn't change the height of the tree. And so there are no changes. This is part of a smaller or a bigger subtree. If this was a subtree of a bigger tree, there wouldn't be any changes on the way back up, okay? That's basically what happens. So you do an insertion, and you have some balance factor changing to do, and the way you can figure out if your subtree has grown is you look at your left or right subtree, whichever direction you're inserting it into, and you look at it before the insertion, look at it after the insertion, and you can tell whether it's grown. Now let's try inserting the 35 into the tree. Okay, just like with a normal binary search tree, we do comparisons and find out where it belongs. In this case, it's going to belong right here. Again, the 37 saw its left subtree grow, so it needs to change its balance factor. It was balanced, so now we make it balanced to the left. The 41 has seen its left subtree grow. Again, by looking at it before the insertion and after the insertion, it was a balanced tree. Now it's unbalanced. That means it grew. So this guy leans its balance factor to the left. The 29 recognizes the 41 has grown in height. It was a right insertion, so we adjust his balance factor to the right. And now the 66 has seen the 29 has grown in height. Now in this particular case, it is already left-leaning. We want to make it more left-leaning. I'm going to mark that red, meaning it's leaning to the left, which means it's an illegal AVL tree. Here we need to do a transformation. Now I happen to know the transformation that we need to do in this case involves making this guy lean to the right, this guy become balanced, this guy become balanced, and then doing what's known as a double rotation. The 41 rotates over its parent and over what was its grandparent. And now we again have a legal AVL tree. We'll talk about the details of how you know what to do when you get something that's too unbalanced a little bit later. And now let's finally insert the 48. Again, the 48, we'll compare, figure out, this is basically just a binary search tree insertion, and we will insert to the right of the 45. The 45 sees its right subtree has grown, so we change that. 66 sees that its left subtree has grown. Well, it was leaning to the right, so now it becomes balanced, and then no more changes up the tree. Okay, so that's basically what happens when we're doing insertions. And the details of how to know what rotation to do and things like that, and how to mark balance factors, we'll look at a little bit later. Okay, now let's do some deletions. Let's try deleting the 91 and see what happens. We do the 91, we do it just like a normal binary search tree to start out with. So we come down here, do comparisons, we find the 91, we delete it. With a deletion, if something changes from non-null to null, like 87's right subtree just did, we need to shift its balance factor away from the deletion because the deletion side has shrunk by 1. And so this guy now becomes balanced. But it's also the case with a deletion, if something has gone from unbalanced to balanced, that means it has shrunk. And so the 66 on the way down would have looked at the 87 and saw that it was unbalanced. And then after deletion would look at it and say, it is balanced. Therefore, it must have shrunk. So 66 needs to shift its balance factor away from the deletion. And so now 66 is a left-leaning subtree. Let's try deleting the 29. Okay, when we do deletions, we are going to do some searches. We find the 29. It's an interior node, and so with an interior node, we need to find the in-order successor. So we go to the right and left as far as possible, which reaches the 35. We'll copy the 35's data there, and now we delete the 35. So 35 gets deleted, but this node sees that its right subtree has gone from unbalanced to balanced. Therefore, it has shrunk. Therefore, this guy needs to move its balance factor away from the deletion, so it moves it to the left. And this guy will have seen something go from balanced to unbalanced. Well, with the deletion going from unbalanced to balanced does not shrink the tree. And so that's all we need to do. So that's what happens deleting the 29. Now let's try deleting the 5. Delete the 5. The 16 sees its left subtree has gone to null. Therefore, we move its balance factor 1 over to the right, which means it goes from left leaning to balanced. The 35 has seen its left subtree go from unbalanced to balanced. Therefore, it has shrunk. I need to move this guy's balance factor 1 to the right, so it becomes balanced. And the 41 now has seen its left subtree go from unbalanced to balanced, so it has shrunk. So it needs to move its balance factor 1 to the right, which in this case means making it right-leaning because it was balanced. And that's the end of that process. Okay, now let's try deleting one more. Let's try deleting the 87. Deleting the 87. Okay, the 66 has seen its right subtree go from non-null to null. Therefore, it needs to shift its balance factor 1 to the left, but it's already left-leaning. I'll indicate that again by red. Now we need to do another rotation. In this case, I happen to know the rotation we need to do ends up saying, let's make 66 balanced, let's make 45 balanced, and do a double rotation of the 48 over the 45 and over the 66. So something like that. Now, the 41 did have a right child that was unbalanced. It now has a right child that is balanced. That means it has shrunk. Therefore, we need to modify the 41's balance factor by shifting it 1 to the left. And so now it is balanced, and this is the resulting AVL tree. In this case, it is totally balanced. It's a full tree. What we have seen are AVL tree operations, insertions, and deletions, and that we insert or delete something on the way back up. We adjust the balance factors. Occasionally, we need to do a rotation or a double rotation, and that's what we're going to talk about now. When we end up having a balance factor that goes off by more than 1, we need to do an adjustment, and what adjustment do you need to do? So we'll look at the various cases here. I've got a little cheat sheet here I've brought along. And these actually are fairly simple transformations. One of the reasons that I like AVL trees, I don't really like AVL trees better than red-black trees, but AVL tree transformations, in my opinion, are simpler. And also, they are the same transformations for insertions and deletions. With red-black trees, you have one set of transformations for insertions, a different set for deletions. Okay, so let's take a look. So in every case, we're going to have something that is out of balance by 1, which is fine. But then we're going to delete something. I'm going to motivate these by deletions. The same situations can come up in insertions as well, but I'm going to motivate these by deletions. That's going to cause the red-black tree to be out of balance by more than 1. Okay, and the node I'm deleting is going to be indicated here in red. Okay, so far, this is a valid AVL tree. This is 1 higher than this, but that's fine. It's marked that way. But now, let's see if we delete the 75. Now, this has gone from non-null to null. Therefore, I need to adjust this guy's balance factor 1 to the left, but it's already left-leaning, and therefore it's out of balance. So what do I do? Well, in this case, what I do is I look, and the top node is always going to be leaning left or right. We're going to have the left cases. The right cases are just mirror images. I'm just going to go through every left case. So in this case, it's leaning to the left, and look at the child. And the child is also leaning to the left. So that is the left case. So that is this case right here. That's in our single rotation category. So what we do is we modify the left to be balanced. So that becomes balanced, and we do a single rotation of the child over the parent. And this gives us valid AVL tree again. Now, it could be the case that it's not as simple a tree as this. There could be subtrees sitting down here, but the subtrees are not going to get modified. Their heights are not going to change, and so they're just going to go along for the ride. And so I've shown the simplest possible case, but there could be subtrees of heights 10. All these guys could be subtrees of height 10, but that won't matter. We won't look at them. We won't touch them. All we do is we do the rotation at the top level. So that was the left case. Now let's look at the left balanced case again. So here we have something. Here the child is not left leaning, it is balanced. So let's see what happens here. So again, we're going to delete the 75. That means that this guy is now out of balance by more than 1. So this is left, and then child is balanced. So let's go to the left and balance case. That says it should be modified so it is left, right, and it's still in a single rotation group, so then we'll do a single rotation. So this guy is going to end up being left. This guy changes to being right, and we do a single rotation. And again, we have a valid AVL tree. Again, there could be subtrees here. They just go along for the ride. Okay, so we've seen left, left. We've seen left balanced. Now let's look at left, right. Now it turns out when you have left, right, you actually need to look at the grandchild as well. So in this case, I have a situation where it's left and then right, and I need to look at the grandchild's balance factor as well. So there'll be left, right, right balanced, and left, right, right. So in the left, right, left case, that is right here, after we do the deletion, this guy recognizes that his balance factor has to be changed to be balanced, which means I have lost height here. This guy recognizes that, so this guy is now marked as 2 out of balance. And that sets us up in this situation. I have left, right, left. I need to change it to right, balanced, balanced. Okay, so right, balanced, balanced. And in this case, I do a double rotation. So I do a double rotation. It's the 60. Moves up above his parent and his grandparent. And here is the resulting subtree. Okay, let's look at the next case. Here I have left, this guy's right, and this guy is balanced. That is the left-right balance case. It becomes balanced, balanced, balanced. Okay, so we delete the 75. And this guy has now become shorter, so this guy now is out of balance by more than 1. So in this case, everything's balanced, balanced, balanced. So that becomes balanced, this guy becomes balanced, and this guy stays balanced, and I do a double rotation. And that is resulting AVL tree. It's a valid AVL tree and is marked properly. And the last case here is I have left, right, and then right. So this guy's left leaning, this guy's right leaning, the grandchild is right leaning. So that ends up being that case. And so I will delete 75. That causes this guy now to have shrunk, therefore this guy is out of balance by more than 1, and we can see that, comparing their heights. And so left, right, right becomes balanced, left, balanced. So this becomes balanced, this becomes left, becomes balanced, and now I do a double rotation. And this is my resulting subtree. And those are all of the cases if it is a left-leaning imbalance. If I have a right-leaning imbalance, we will not go through those, but those are just the mirror images. Okay, so these two are the single rotations, left, left, we have left, left, and left balanced. These are just the mirror images of those. These are the 3 we just saw, and those are the mirror images of those. And so this is our cheat sheet that tells us what rotation and what balance markings to make on everything. Okay, now let's look at this in action. We'll start with a relatively small example, just a handful of numbers. And following that, we'll do a larger example. Whether you want to stick around for the entire large example is totally up to you. But I'm going to start with a small example that hopefully handles most of the cases. So let's start. So I'm going to start with the 59. Becomes the root, then 52. Gets inserted into the left child of 59. But the 59 has now seen the 52, its left child rather, has gone from null to non-null, therefore adjust this balance factor to the left. We now have the 5. The 5 ends up getting inserted as 52's left child. 52 sees his left subtree has gone from null to non-null, so it grows. The 59 has seen the 52 go from balanced to unbalanced. It has grown. Need to adjust this guy to the left, but it's already left leaning. Therefore, we have to do a transformation. In this case, the transformation, we're left, left. I look at left, left. It says switch it to balanced, balanced, and it's in the single rotation category. So I make them both balanced, do a single rotation, and there we go. Now let's draw the 53. 53 ends up getting inserted into 59's left subtree as 59's left child. But the 59 has seen its left subtree, its left child, go from null to non-null. That increases its height of its left child, so I switch the balance from balanced to left leaning. But now the 52 has seen 59 go from balanced to unbalanced, so it has grown. So 52 needs to adjust its balance factor to the right. It's balanced, so now I make it unbalanced, and there is my adjustment. There's the current AVL tree. Let's try 35. 35 ends up being going as 5's right child, but 5 sees that its right child has grown, and 52 sees that its left child has grown. Well, 52 was right-leaning, so it now becomes balanced. Now we go to the 9. The 9 ends up becoming 35's left child, but we see his left child has grown, so we adjust this balance factor. 5's right child has grown, adjust this balance factor, but it's already leaning to the right. Therefore, we have right, left, balanced. So that's this case. Right, left, balanced becomes balanced, balanced, balanced. And so we adjust these two guys. This is balanced, 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 and we do a double rotation of the 9 over both its parent and its grandparent. And this is the resulting AVL tree. Now let's try inserting a 2. A 2 ends up coming down with comparisons, and it becomes the left child of the 5. But the 5 sees its left child has grown. The 9 now sees its left child has grown, and the 52 sees that its left child has grown. And so this is the resulting AVL tree. Now we look at a 15. Insert a 15. That ends up becoming the left child of the 35. So 35 sees its left child has grown. 9 sees its right child, his right child has grown, so adjust from left to being balanced, and that's the only adjustments needed. 18, insert the 18. It will end up getting inserted as the right child of the 15. 15 has seen that his right child has grown, so adjust its balance. 35 sees his left child has grown, but it's already left leaning. Therefore, we have left, right, balanced. Left, right, balanced is right here. It turns into balanced, 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 so everything becomes balanced, starting with the 35. And I have a double rotation to do. Now I have a 33. 33 ends up coming down here and becomes 35's left child. 35 sees that 33 has gone from null to non-null, so it adjusts its balance factor to the left. 18 sees growth to the right, adjusts its balance factor to the right. 9 sees growth to the right, adjusts balance factor to the right. And the 52 has seen growth to the left because 9 had been balanced, now it's unbalanced. So I need to adjust this guy to the left, but this guy is already left leaning. And so in this case, I have a transformation to do, and I have the left, right, right case. So there we have the left, right, right case. So I turn that into balanced, left, balanced. So balanced, left, balanced, and now do a double rotation. And this is my resulting AVL tree. Now let's try the 42. It is going to insert into the 35's right child. So 35 sees growth on that side, therefore I adjust the balance factor so now it's balanced. Insert 97, that goes way over to the right here. Again, that 59 sees growth on its right side, so it goes from left to being balanced. And 40 ends up being the left child of the 42. 42 sees growth on its left side. Therefore, 35 sees growth on its right side. Therefore, 52 sees growth on its left side. Therefore, 18 sees growth for its right side. And this is the resulting AVL tree. Okay, so now we've done the insertions. Let's try to do some deletions. Okay, so what I'm going to do is I'm going to start by deleting the 59 and deleting numbers in order as we go lower. So 59, 53, 52, et cetera, et cetera. So the 79 is going to not get deleted, but otherwise we're going to delete from right to left or from highest to lowest. Okay, so the first thing we do is we want to delete the 59. Well, it's an interior node, so I take its in-order successor, which is the 97, and copy its data there. The 97 now gets deleted, and that means that this node has seen its right child reduce in height by 1, therefore I adjust the balance factor like that. Next thing we do is we delete the 53. Well, the 97 has seen its child go from null to from non-null to null, therefore adjust its balance factor. But this guy has gone from unbalanced to balanced, therefore this guy has shrunk, therefore this guy needs to adjust his balance factor to the left, away from the deletion. But it's already leaning left, so what do we see? Left, right, left. Left, right, left says we should change that to be right, balanced, balanced. So I was doing this at the 52, so left, right, left becomes right, balanced, balanced. So right, balanced, balanced, and I do a double rotation. Okay, now the 18 has seen its right child, which had been unbalanced, go to balanced, so the 18 needs to adjust its balance factor 1 to the left, away from the deletion, and so it becomes balanced now. Okay, now let's delete the 52. If I delete the 52, there's the 97. This guy has, 42's right child has gone from unbalanced to balanced. That means it's shrunk. Therefore, I adjust 42's balance factor to the left. That's all we need to do there. Now we delete the 42. Well, 97 is in our successor. So I will copy the 97 there. But this guy has now gone from non-null to null. So this guy's a balance factor, 97's, the new 97, so to speak, needs to adjust its balance factor 1 to the left, but it's already left leaning. Therefore, I need to look left balanced. Okay, so left balanced becomes left right. Left balanced becomes left right. And then I rotate, it's a single rotation, and that ends up giving me my new AVL tree. Now I delete the 40. Oh, we have seen the 97 has reduced in height. Therefore, we need to adjust 35's balance factor. But 35 now is reduced in height. It went from unbalanced to balanced. Therefore, we need to adjust 18's balance factor. And that's the final result after the deletion. of the, what, 40, I think it was. Okay, now we'll delete the 35. 35, in order successor, 97. So we delete the original 97. But this guy has shrunk on its right side, therefore I need to adjust it to be left-leaning. And that's all we do there. Now we delete the 33. The 33 is deleted, and the 97 sees its its left child shrink. Therefore, I need to adjust its balance factor back to be balanced. But this has gone from unbalanced to balanced. Therefore, this guy knows its right child has shrunk. Therefore, I need to do an adjustment of this guy to the left, but it's already left-leaning. Therefore, I have a left, left, which is this case, switch to balanced, balanced, and do a single rotation. So switch to balanced, balanced, and do a single rotation. There we go. Now let's delete the 18. In order successor replacement, delete the original. This guy has gone to null, therefore adjust the balance factor to the left. Done with that. 15, delete that. This guy has seen its left child shrink, therefore it becomes balanced, but it has become balanced, therefore this guy knows it has seen its right child become reduced in height by 1, therefore it needs to adjust its balance factor 1 to the left, which we do. Now let's delete the 9. The 9, in order successor, since interior node, delete the original 97. This guy has shrunk to the right, adjust its balance factor to the left, but it's already left-leaning. Therefore, we have to do a transformation. It's left, left, which is this one right here, left, left. Therefore, we change it to balanced, 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 do a single rotation. There we are. And now let's delete the 5. It's an interior node. Do the in-order successor replacement. Delete the original. This guy has just gone to null. Therefore, I adjust this guy's balance factor to the left, which gives me that. And finally, I delete the 2. Well, this guy, his left child, has gone from non-null to null. Therefore, adjust this balance factor 1 to the right, which makes it balanced. And there is our final AVL tree. Now we'll do a larger example. In this case, I will have a series of numbers in the 100s, followed by a series of numbers in the 300s, and then a series number in the 200s. So it's going to intentionally be built so if we weren't doing any rebalancing, it would become an unbalanced tree. And so the 100s will give us a subtree, and when we start doing the 300s, they're going to all go off to the right of the 100s. And once I have that, we're going to be inserting some kind of into the middle. So let's see what happens here. Okay, we'll start out with 199, then 184. I'm going to do this rather quickly. I'm not necessarily going to be looking every time at, what rotation to do. I'll just kind of mention the rotation, and you can kind of use the legend over here as a reference. Okay, so 184, it has grown, so 199 becomes left-leaning. 111. 184's left child has grown, becomes left-leaning. 199 sees 184 has grown, it becomes left. It needs to lean left to the more, but it's already leaning left. Therefore, we do the left-left rotation, which makes these balanced. Single rotation. There we go. 170 ends up inserting right here. I see tree size increases, actually all the way up. 102 ends up going here. That has grown, therefore this guy goes from right to balanced. 123 becoming here. So I see growth here, here. This guy needs to grow, but it can't grow anymore. It can't lean anymore, and therefore I have a left, right, left. That becomes right, balanced, balanced, and double rotation. Insert the 100, comes down here. And I actually see a height increase all the way up on the left side. Now we'll start inserting the 300s. 392, one getting inserted here. So this guy has grown. This guy has seen that his right subtree grown. It's already right leaning. Therefore, I need to do a right-right transformation. That involves making these guys balanced and doing a single rotation there. 310 ends up inserting right here. So I get growth, growth, and this guy was left leaning and now becomes balanced. 347 ends up going there. So I grow there. This guy can't grow anymore, therefore I have a left-right balanced transformation, which is make these two guys balanced and do a double rotation. 314 ends up going right there. And so I have a increase height here, here, and now I can't make this guy any more right leaning. I have a right, left, right, which becomes left, balanced, balanced, and a double rotation. 351 ends up going as a left child of the 392, and I actually see the height growth propagate all the way up. 365 ends up being the right subtree of the 351. So I see growth there. I can't make that any more left leaning. I have a left-right balanced rotation transformation. That is making these two guys balanced, and this guy is a double rotation. 369 ends up going as the left child of the 392. So I see growth, growth. Here, this guy's already right leaning, so I have a right-right transformation on 347. That ends up making those two guys both balanced and doing a single rotation. 335 ends up coming right down here. And I see height growth, height growth, height growth. But here, I'm already right leaning. I can't go any farther. I have a right, left, left. That ends up becoming balanced, right, balanced, and double rotation. 340 comes down right to there. Grew on that side. This is already right leaning. I have a right-right transformation, which is make those two guys balanced and do a single rotation. 338. Gonna come right down here. And I will have growth. I'm going to see the tree growing all the way up. And finally, I get here, I can't make this guy go any more to the right. I have a transformation, which is going to be right, left, right, which is left, balanced, balanced, and do the double rotation on the grandchild. There we go. And here's a 305, which will end up coming as the right child of the 199. That simply makes this the 199 balanced. Okay, I've inserted the 100s and the 300s. Now I'm going to insert some elements in the 200s and see what happens. So 259 is going to end up going right there and propagate height growth here. But now I just need to adjust this guy from left to balanced, and I'm done. 204 ends up coming down here. And height growth here, already left leaning. This is a left-left transformation. So make these two guys balance and do a single rotation. 225 ends up coming right down there. So I have left, increase height to the right. I'm out of balance by more than one here. I have a right, left, right. That becomes a left, balanced, balance, and a double rotation like that. 270 ends up coming as a left child of the 305. I propagate the height up. In this case, the height propagation goes all the way up to the root. I now have 268. Do some comparisons, and 268 is going to end up going right there. Propagate the height up. Can't propagate anymore because it's already left leaning. That is a left, which gives me that. 277 ends up becoming the left child of 305. So I propagate the height up. Already right leaning here. I have a right, so that ends up being a single rotation. The 241 comes as a left, or so the right child of the 225. Propagate the height up, height change up. I now have a imbalance of more than one, and so I have a right, left. That becomes a balanced, right, balanced, and a double rotation. I now insert the 249, which ends up getting inserted right here. Okay, that quickly bumps into this guy that's already right leaning. That's a right. So I change those guys to balanced and make it a single rotation. 234 comes down right to there. And I propagate the height increase up quite a ways, but I finally get to already right. The 170 is already right leaning. This is right, left. That ends up becoming left, balanced, and a double rotation. 224 ends up becoming the left child of the 225. So I just need to make the 225 balance now. 223 is going right to the left child of the just inserted 224. Propagate the height increase up. I hit the 241, already left leaning. This is left, so I just do the single rotation. 218, that becomes the left child of the 223. So it increases in height. Can't make this any more left leaning. I have a left transformation. 235 ends up becoming a right child of the 234. Propagate the height up here and keep propagating the height, and it keeps propagating. As long as things are balanced, it keeps propagating, and I end up getting way up to the 310. This is left, right. That turns into right, balanced, and a double rotation. So there is my transformed AVL tree. 292 comes down, and it looks like it ends up there as a right child of the 277. And so that height propagates up. But now I have the 305, which is already left leaning. This is a right-left balanced, so those two become balanced. And I do a double rotation. 271, that will come right here, left child of the 277. So propagate the height up. There's where the propagation stops. This guy's already right leaning. I have a right, left at the 270. That means I need to make this balanced, right, balanced, and do a double rotation. I have 254, which is going to end up going right down there after a few comparisons, and propagate the height up here. This guy is left leaning, he becomes balanced, and I am now done. Okay, now we've created this AVL tree, let's do some deletions and pretty much destroy it. What I'm going to do is I'm going to do deletions basically of everything below 350, starting at the highest numbers. So that would be the 347. These guys are all above 350, so I'm going to start at 347 and just go down numerically from there, and we'll see what happens. Okay. So 347 is an interior node. In order successors of 351. So I copy the data. Copy the data there. Delete the original 351. And what that gives me is a 365 sees that its left child has shrunk. It's already right-leaning. I want to make it more right-leaning. This is the right-left balance case, and that becomes everything balanced. This guy ends up now doing double rotation, but now the node in this position has changed from unbalanced to balanced. Therefore, this guy needs to adjust away from the deletion to the left. And so that's our final result after that. Okay, let's delete the 340. 340 is deleted. This guy sees that his right child has shrunk, therefore adjust this, but that means this guy has shrunk, so I adjust that. But that means this guy has shrunk, so I adjust that. And that means this guy has shrunk, so I adjust that. Okay? And we can see that this subtree is higher than that subtree, so that ends up being correct. Okay, let's delete the 338. Delete the 338. Well, that just is an adjustment. This guy needs to adjust to the left, which it does. Now delete the 335. The subtree, the left subtree of the 351 has gone from unbalanced to balanced, therefore it has shrunk, so I need to adjust the height to the balance to the right. There we go. And now the 314 goes away. Well, now I have deleted the 314. This guy has gone from non-null to null. This guy needs to adjust his balance to the right, but it's already right-leaning. That gives me the right balanced case, which turns into the right left case with a single rotation. There we go. Okay, now I want to delete the 310. Well, it's an interior node, so I do the in-order successor, which is the 351. And now I delete the 351, the original 351, which causes this guy to shrink. So this guy needs to adjust its balance factor. But now this guy's balance factor is adjusted to be balanced. So that means there's a shortness coming up here. So this guy needs to adjust. So 351 here needs to adjust its balance factor to the left. Delete the 305. That means the 292 has shrunk, and that means the 277 needs to adjust its balance factor like that. Now delete the 292. I see shrinkage here. This guy cannot go any more to the left. I have a transformation to do. This is the left-right transfer, so the left balance transformation, which becomes left-right and a single rotation like that. Now delete the 277. 277 gets deleted. This side has shrunk, therefore this guy needs to adjust its balance factor to be balanced, which means this guy has shrunk, which means this guy needs to adjust its balance factor, which means this guy has shrunk, which means this guy tries to adjust its balance factor, but it is already unbalanced to the left. Therefore, I have a left balance transformation to do, which means leave this guy left, make this guy right-leaning, and do the rotation like that. So 204 is now our root. Okay, now let's delete the 271. 271 is deleted. Well, that just means this guy's balance factor needs to be adjusted. Now delete the 270. Oh, this guy in this position has gone from unbalanced to balanced, therefore this guy's balance factor has to be adjusted. Now delete the 268. Again, I see a shrinkage on the right. This guy needs to adjust, but it's already right-leaning, therefore I do the right balanced transformation, which means mark this guy's left-leaning, do the single rotation, and there we go. I now need to delete the 259. Its in-order successor is the 351. So I move the 351's data up there and delete the original 351. But this guy has shrunk, therefore this guy's balance factor has to change. And what that means is this guy has shrunk, has gone from unbalanced to balanced, therefore this guy's balance factor has to change, but this guy is already left-leaning, Therefore, I need to do a transformation. This is left-right balanced. So left-right balance says change to balanced, balanced, balanced. And so like that. And now this guy ends up being a double rotation like that. But now this guy's right child had been unbalanced. Now it's balanced. Therefore, this guy has shrunk. Therefore, this guy needs to adjust his balance factor 1 to the left, which is like that. Okay, delete the 254. That means this guy has shrunk. Therefore, I need to adjust this guy's balance factor like that. Now delete the 249. This guy has shrunk. It's already right leaning. I need to do transformation. The transformation is it's left balanced. Or sorry, it's right balanced. Now it needs to be right left and a single rotation. Now delete the 241. Well, the 351 is its in-order successor, so I copy its data there. I delete the original 351. This ends up seeing shrinkage on the left. Therefore, this guy's 369's balance factor has to adjust to be balanced, but that means this guy has shrunk, so this guy's balance factor needs to adjust 1 to the left, and that is the result there. I now delete the 235. 235, deleting, but that means this guy needs to adjust to be balanced, which means it is shrunk, so this guy needs to adjust from balanced to left leaning, and there we go. 234, delete that. It is shrunk. I need to adjust this guy to the 255 to the left, but it's already left leaning. Therefore, I have a left balanced, which turns into a left right with a single rotation. Now we delete the 255. 255 is deleted, and 233 sees that its right child has shrunk. Therefore, it changes its balance factor to be balanced, but that means that 351 is seeing 223 as being shrunk, and 204 is seeing 351 as being shrunk, so ultimately 204 ends up becoming left leaning. Delete 224, just means 223 needs to become left leaning. Delete the 223, that means the 351 needs to become right leaning. Delete the 218, I want to make the 351 even more right leaning, but I can't. And so I need to do an adjustment. And this is the right balanced case, which becomes right left with a single rotation. And now I want to delete the 204. Well, the 204 is an interior node, so I take its in-order successor by going right and left as far as possible, which is the 351. And so 351's data gets copied there. Delete the original 351. That means that this guy has shrunk, so this guy needs to adjust to be 1 more to the right, which makes it balanced, which means it has shrunk, so this guy needs to adjust 1 more to the left, but it's already left leaning. Therefore, I do a transformation, which is the left-left transformation, so that changes those guys to balanced and does a rotation like that. Okay, delete the 199. Well, that means the 351 sees its left child has shrunk, so it adjusts its balance factor 1 to the right. 184 is deleted. 351 again sees its left child shrunk. This time it's already leaning to the right. I do this transformation, which is the right balance transformation, which means I mark this guy as being left leaning and do a single rotation. Now I want to delete the 170. It's an interior node, so I copy its data, or the 351 data is in-order successor 351, and delete the 351. But that means that this guy has seen shrinkage, so I make it go from left leaning to balanced. But that means this guy sees this guy has shrunk, so I need to mark this guy as left leaning. Delete the 123. Okay, delete the 123. It is seeing something go from non-null to null. Therefore, it needs to make this guy more left leaning, but it's already left leaning. Therefore, I need to do the transformation. It's a left-left transformation. Therefore, I make those guys balanced, and I do the rotation. But now this guy's in this position, this guy's left child has gone from unbalanced to balanced, which means that This guy needs to adjust its balance factor 1 to the right, so it goes from left leaning to balanced. Now delete the 111. See shrinkage here, do the adjustment there, delete the 102. I see shrinkage to the right, adjust the balance factor to the right, and finally delete the 100. And I want to adjust 351's balance factor to the right, but it's already right leaning. Therefore, I do the right balance case, which is this, turns into right left, and single rotation. And there we go, and there's our tree with all the smaller numbers deleted. If I want, I can continue. Let's just delete this guy. This guy now from highest to lowest, so 392 gets deleted. So shrinkage coming here. I want to make this guy more left-leaning, but it's already left-leaning, so this is the left-right balance case, which basically makes everybody balanced and does a double rotation. 369. Well, that makes this guy become more left-leaning. And finally, I delete the 365. 351 is by itself. I can delete that, and now I am really done.